a couple people disenrolled in the class, so the enrollment started falling again. So maybe it was not necessary, but anyway, I think this space is a lot more comfortable. Certainly there's more board space, which is good. I don't have a whole lot by way of announcements. You know, we have homework 1 due tomorrow, right? I have office hours after class if you want to chat about that. Lab 1 due next week. Of course, you can use lights if you want, turn it on Monday instead of Friday. Remember to join the Piazza site. So the Blackboard site, you're enrolled in automatically when you enroll in the class. Piazza, it's not set up to do that. There might be a way of doing that. If there is, I don't know how to do it. But anyway, so you have to go in and manually add yourself. Do ask questions on the Piazza site. It's a good way of getting questions answered. We're still waiting for our inaugural question on the Piazza site. So some daring person can do that. Tomorrow, the discussion session will be just probability review. So Umair has various probability exercises, basic probability exercises that he'll pose, and you can work through with him if you like. It's optional. I've not posted any lecture notes yet. I will start doing that probably over the weekend. Any questions? Good? Okay. So today I'd like to finish talking about Gaussian random variables, and then we'll switch to the other half of our probability background section, which is Bayesian inference. So let's recap where we were with Gaussian random vectors. So first of all, I left a little gap here because I want to write up one new fact that's just kind of useful for when you're dealing with Gaussian distributions. So remember, in a prior lecture, we defined what it means for a matrix to be positive semi-definite. Okay, and we defined what it means for a matrix to be positive definite. Okay, so it turns out if a matrix is positive semi-definite and invertible, so non-singular, then it is positive definite. And if it's positive definite, then it's positive semi-definite and non-singular. Okay, so this is it's not really that hard to show. It's kind of a linear algebra fact. So basically, I mean, just use the fact that the determinant is the product of the eigenvalues. So when you do your expansion, your U lambda U, the eigenvalues are sitting there along that lambda matrix. Okay. So if it's positive semi-definite, those are all non-negative. If the determinant is not 0, that means none of them are 0. That means all the eigenvalues are positive. This. Okay. Whereas if you have this, then all the eigenvalues are positive, so they're all non-negative, and their product is not 0. Okay. So that at a high level, that's the way that goes. This is not like a super critical fact, but it just simplifies the discussion a little bit about Gaussian random vectors. So anyway, I don't think I stated this explicitly in a prior lecture. I probably should have, because the second parameter in the Gaussian random vector density is a positive definite matrix, and we use the fact that it is invertible. So let's go through the definition. I'll show you what I mean. Okay, so we work a lot with Gaussian distributions in this class. Hopefully you've seen the Gaussian distribution before in a prior class. As I've said before, we don't tend to operate with individual random variables in isolation in this class. We tend to have a whole bunch of them that we're working with at once. And it's helpful to put them in a matrix, or put them in a vector, and then you can manipulate them using linear algebra techniques. Okay, so we tend to work a lot with random vectors as such. So given how prevalent the Gaussian distribution is in practice, and given what a great analytical tool it is, and given that we tend to use random vectors in this class a lot, it makes sense to look at Gaussian random vectors. Okay, so with that as motivation, we'll define a random vector x to be a Gaussian random vector with two parameters, mu, which is just a vector in Rn, and k, a positive definite matrix. Okay, if x is continuous, meaning it has a density, and its density has this particular form, which is the multivariate Gaussian distribution you might have seen in a prior class. If you haven't seen it, then just take this as the definition. Okay, so if the density is of this form for some particular k that's positive definite and some vector mu, okay, then we'll say it's Gaussian. And you can verify that when x is a scalar, okay, when n is 1, when the dimension is 1, this whole thing collapses down to just the familiar Gaussian density that you know. Okay. So the reason I mentioned this point here is that we have k inverse sitting right here, right? So k has to be invertible. And this k matrix here has to be invertible for this even to make sense. Okay, and turns out we haven't seen this yet, but it turns out this is the covariance matrix of the vector. We don't know that yet. Okay, but that's coming up. So given that it's a covariance matrix, you expect to be positive semi-definite. Okay, but then we also need to be invertible for this density even to make sense. Okay, so the relevant condition is required to be positive definite, positive semi-definite, and invertible. Okay, so you can write it like that if you want. I mean, that's logically the same thing, but this is just a lot simpler, a lot more compact. Okay, speaking of compact, so all this stuff here, Gaussian random vector with parameters mu and k, okay, we just write like this. All right, this is pure shorthand, just so we don't have to write all this all the time. Just abbreviate it like this. Okay, so we read this as Gaussian, or x is Gaussian, or distributed as a Gaussian distribution with parameters mu and k. Okay, so this is a rather complicated formula. We want to get kind of a mental grasp of it. So I did a couple of examples last time. We'll finish the second example and then do one third example today. So first example, let's suppose I have a random vector x, and suppose the components are IID, so independent, that's the first I, identically distributed. Okay, so they're independent, they all have the same distribution. Suppose that distribution is Gaussian scalar, okay, with zero mean and unit variance. Okay, so we write that, you know, using similar notation, a Gaussian scalar with mean 0 and variance 1, you write as the script n 0, 1. Okay, so it's like, you know, you call rand n in MATLAB a bunch of times, you know, like 10 times, you get 10 numbers, you put them in a vector. Okay, that is a random vector, right? It's a vector, the components of which are random variables. Okay, what can we say about the distribution of that? Well, we wrote down the distribution of that x so obtained last time. This is what we got. Okay, so if you just pattern match, okay, the mu is 0 and the k is identity, right? Okay, so indeed, if you just take a bunch of independent Gaussian random variables, throw them in a vector, you will get, by our definition, a random vector. Okay, and the parameters will be the 0 vector and the identity matrix. Okay, and we call this a standard normal random vector. We call a random variable, a Gaussian random variable with 0 mean unit variance, a standard normal random variable. Okay, so that's one example. Okay, second example, suppose x has independent components, but they're not identically distributed anymore. They're all Gaussian, but they have varying means and variances. So each one has its own mean, each one has its own variance. Okay, before they were independent and they all had the same mean, namely 0, and the same variance, namely 1. Okay, now they're still independent, they're all still Gaussian. Okay, but the mean is different across the components and the variance is different across the components. Okay, so being independent, the density of the vector, which is nothing but the joint density of the components, is just the product of the marginals. So we roll that out and put it in this form, and this is where we left off at the end of last lecture. And I was trying to convince you that this is a valid Gaussian density of this form right at the end of the last lecture, and I was trying to kind of cram it in right at the last minute, or even over the allotted time, which is never a good practice. So let's pick it up right here. Any questions up to here? Good? Okay. So the claim is that this is indeed a valid Gaussian density, and I think the easiest way to see it is just for me to tell you what the k and the mu is, and then, or r, and then you can just check it yourself. So once you have it in this form, you can conclude that x is Gaussian with mean mu and, sorry, with first parameter mu, second parameter k. We don't know that's the mean yet. We will shortly. Okay, first parameter mu, second parameter k, where, okay, these are not defined yet. Right, mu, the vector, is just mu 0 through mu n minus 1. Okay, and k is just the diagonal matrix consisting of all these different sigmas squared. Okay. So I'm not going to try to show that. I mean, you have to just kind of stare at it. So just take this formula, plug in the k, plug in the mu, okay, and then, you know, just simplify it using the fact that k is diagonal. I'll collapse down to this. I mean, the determinant of this is just the product of the sigma squares, right? So that's pretty clear. And this one, you got to just kind of stare at it, do the matrix multiplication in your head. Okay, so that's another example. Let me show you the third, and this is the most important of the bunch. Okay, so example 3. Okay, so let's start with a standard normal random vector. So let Z be standard normal random vector. Okay, so parameters 0 and I. Let's suppose A is a square and invertible matrix. Let's suppose B is just some vector. Okay, let's consider X, which is defined to be A, Z, plus B. Okay, so you run rand-n a bunch of times in MATLAB. Okay, you get a standard normal vector, right? You get a vector Z, the components of which are all IID standard normal, right? I have that vector in MATLAB. I multiply it by A, and I add this fixed vector B to it. Okay, I get a new random vector, right? X is a random vector. It's just a vector whose components are random variables, right? They're like derived functions from these random variables that comprise Z, right? All right, is this a Gaussian random vector? Let's see. So is X Gaussian in shorthand form? Okay, so we need a formula for the density of Z, or the density of X, right? That's how we, with our definition, you got to just check, like, is the density of X of this form, right? So we need the density of X to see if it's in that form. So for this, we need a way of converting the density of Z, which we've got. That was like right here, right? I mean, this X is the Z over there has the same density of the X in example 1. Maybe I should have just used Z in this example to begin with. So imagine just calling this Z here. So Z, 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 Z. You don't have to change your notes. I'm just for easy comparison. Okay. So the Z in here, this Z has this density here. Okay. So now I need a formula for relating the density of Z to the density of X. And then once I have density for X, I can pattern match with this, right? Okay. So the fact relates the density of X to density of Z. And I need Z, I guess, in terms of X. So X minus B times A inverse, like that. Okay, so remember, facts are things I don't prove. Theorems are things we prove in the class. I'm not going to prove this mainly because in my mind this is an ECE 3100 level fact. Okay, this has nothing to do with digital communications, not anything to do with Gaussian vectors and facts. It's just like you have a joint density of some random variables, you put it through this linear map, and you want the joint density of the output. Okay, so you may or may not have actually covered this in ECE 3100. Some instructors would cover it, some would not. If you've seen this before, great. If not, don't worry about it. Like, we're going to use it this once here and then probably never again. So as long as you understand what it's saying, it's relating the density of X to the density of Z, then you're good to go. Given that we have so much board space, maybe I'll leave the definition up. Incidentally, if you've ever seen this, you might have seen the scalar version of this. So if you have like X is AZ plus B, the density for X in terms of the density for Z. With 1 over A. Have you seen that before? Yeah? Okay. If not, it's not too hard to derive this. Like, just write down the CDF for X, plug in, in terms of Z, okay, and then express in terms of CDF of Z, and then differentiate. You can get something like this. So it's not too hard. And this is like the multivariate version of that. Okay. All right, so if I use this fact, what do we get? So density for X is going to be 1 over determinant of A, which is non-zero since A is invertible, so that's good. And then F of Z I've got up here, right? Here's FZ. It's the density of a standard normal random vector, so 2 pi n over 2. e to the minus 1/2. And then in place of z, I'm going to have this argument here. A inverse x minus b. You have that whole thing transpose. And then the same thing again. A inverse x minus b. Yeah? Yeah?
When you write 1 over a, you should have a b.
Yeah. I should have like Hershey's Kisses and I throw them out whenever someone catches a missing underline. Yeah, good. Okay, so does this work? Let's see. So we got the 2 pi. That's a good start. We have determinant of a here, and I want like a square root of a determinant, so that's potentially an issue. Let's keep moving for a moment. AB transpose, B transpose, A transpose, right? So this is x minus B transpose, A inverse transpose, A inverse x minus B, right? What do you think? Gaussian? Yes or no? And if so, what are the parameters? I mean, the first parameter you can take a reasonable guess at, right? The mu parameter. What would you guess? Say something. Yeah, B. That's a reasonable guess. Okay. This looks fine. I got, if you pattern match here, like something, I got to figure out what's going on there, and I got to figure out what's going on here, right? This one, one way of kind of massaging this into this form is to say, assuming everything's invertible, A, B inverse is B inverse A inverse, right? So I can write this as A transpose inverse, right? And then I have something inverse, like I have there. I want, whatever I've got there, I want, without the inverse, I want the determinant of that square root here, which is actually what I have, right? Because A, can you see if I write down here? No, okay, everyone cranes their necks to see. This A, right here I've got A transpose, right? I can write that as A, like that, certainly, right? And then A and A transpose have the same determinant, right? And then determinant of the product is product of the determinant, so A transpose determinant, like that, right? And so that's my K. My K is A transpose. So yes, X is Gaussian with parameters B and A transpose, okay? And remember I said we don't know yet that this is the mean and the variance, but we'll show it shortly. If you want to cheat a bit, okay, then you want to figure out what the parameters have got to be. Well, I mean, if you look at this, the mean of X has clearly got to be B, right? Because that's mean 0, right? And if the covariance matrix of X is K, what is the covariance matrix of, so if the covariance matrix of Z is K, what is the covariance matrix of X? Like the one formula I suggested you memorize? You can flip, it's okay. A transpose, right? So in our case, K is identity, so just get A transpose as the covariance matrix, right? So if you cheat a bit and just say, well, I know this is going to be the covariance matrix, then you can postulate, what should go there. Okay. Okay, so to steal a line from one of my colleagues, this is not just an example, this is the only example. Okay, this is the only way you can get a Gaussian vector, is to start with a standard normal and apply a linear transformation to it. Okay, i.e. every Gaussian vector whose density has this form can be expressed in this form for some A and some B. Okay, so I'd like to show you that. It's a useful derivation to go through, useful in many ways. Okay, so that's basically what I'm going to show you next. Okay, so that example is done. So yes, this is a Gaussian vector. And next I'm going to show that any Gaussian vector can be derived in this way. Okay, to do that, we have to do a little bit of a linear algebra aside and talk about matrix square roots. Or matrix square root. Okay, so here's my question. So let's suppose K, suppose you're given a positive semi-definite matrix, K. How should we define K square root like this to the power 1/2? Okay, I mean, what meaning should I attach to this? Okay, I mean, we know what that means, right? Like you take the matrix and multiply it by itself. I know what that means. Do it again, right? What's that? What do I do with that? Okay, so given K, we want to define a matrix that we're going to call this. Okay, just have the property that when you multiply it by itself, you get K back. All right. This is not possible for like every possible matrix, at least if you want to work within the reals. I mean, like here's a matrix, you know, there's no square root of that, unless you allow for complex numbers, right? So it's not possible always. But when we have an arbitrary matrix, we have a positive semi-definite matrix. Okay, so it is possible. First thing to note, okay, is that taking the square root component-wise is not going to work. Okay, don't just take K and take square root of each component. Not going to happen. I mean, okay. I mean, I guess you can do that. Well, I don't know. I mean, actually, K can be positive semi-definite and have negative entries. Like this is a positive semi-definite matrix right here. Okay, so again, unless you're dealing with complex numbers, you can take square root component-wise. Even if, you know, that's also positive semi-definite. But if you go through and just take square root of everything, this matrix times itself does not give you the 1, 1/2 back. Okay, so just taking component-wise operations not going to do what we want. So the trick is to use our expansion for K. Okay, so let's recall our fact about K. Okay, so K is positive semi-definite if and only if K can be written as U lambda U transpose, where U is a matrix whose columns is an orthonormal basis. Okay, which implies that U transpose is equal to U inverse. And the terminology people use for this is they say U is an orthogonal matrix. And then lambda, that capital lambda there, is diagonal with non-negative entries. So lambda is lambda 0 through lambda n minus 1. It's diagonal. And lambda I is going to equal to 0 for all I. I think I've introduced this abbreviation before, right? For all. You've probably seen it before. It's for all. I'm not fond of this terminology, by the way, orthogonal matrix, because in order for a matrix to be orthogonal, its columns have to be an orthonormal basis. So they have to be a basis and an orthogonal one, and they need to be normalized so that they have length 1. So if I was inventing the terminology, I would call this an orthonormal matrix. And an orthogonal matrix would be one whose columns were orthogonal but not necessarily normalized. But this is the terminology people use, so we'll stick with it. But bear in mind, an orthogonal matrix actually has orthonormal columns, not just orthogonal columns. OK. One other point that I didn't emphasize last time I wrote this up, if and only if. OK, so if k is positive semi-definite, then this is true. If k can be written this way, then it's positive semi-definite. All right, so back to matrix square root. So I'm given k. I know k can be written like this. I want to define a square root. So here's what we'll do. So given k, positive semi-definite, such that k is u lambda u transpose, like over there, we define square root to be u lambda to the 1/2 u transpose. This should set off alarm bells in your head when I write that. Okay, the mental compiler you have running should hit this in the right-hand side and say syntax error. Or I don't know, type invalid or something, right? Why? Why is this no good? Yeah?
The square root of a matrix.
Yeah, we're defining square root of a matrix in terms of square root of a matrix. That's the whole point of this definition, is to define what it means to talk about matrix to the 1/2, and I just defined it in terms of itself. But it's diagonal, right? There's an easy patch for this. Okay, so if I have a diagonal matrix, it's pretty clear. A diagonal matrix with non-negative entries is pretty clear how to take the square root, right? Just take the component-wise square root, and it will work in that case. So 1/2 is just lambda 0, lambda 1 through lambda n minus 1, all with the square root just component-wise. OK, so this matrix times itself is definitely lambda. OK, so it's like a bootstrapping procedure. So define square root first for diagonal non-negative matrices. OK, and once you've done that, then you can define it for arbitrary positive semi-definite matrices. All right, so a few notes on this definition. First of all, does it work? I can write k superscript 1/2 equals blah, blah, blah. There's no guarantee that the blah, blah, blah squared equals k. So our first thing to do is just check that. So k to the 1/2 times k to the 1/2. Just plug in u lambda 1/2 u transpose, u lambda 1/2 u transpose. Right? Tell me about u transpose u. It's identity, right? Because it's an orthogonal matrix. So u lambda to the 1/2, lambda to the 1/2 u transpose. Here I have lambda to the 1/2, lambda to the 1/2. So that's just lambda u transpose equals k. It works, right? What can we say about the determinants? So just take determinant both sides of this equation, and you get determinant of k to the 1/2 times determinant of k to the 1/2. That's determinant of k, right? So what do we conclude from that in words? Like in English, the determinant of the square root is what? Yeah? So in English, the square root of the determinant equals the determinant of the square root. All right, 3. If k is invertible, i.e. it's positive definite, not merely positive semi-definite, then the square root is also invertible by this reasoning right here. And in fact, we can get a formula for the square root, or for the inverse of the square root. Let me think about, I guess you just do this. So in fact, we can say what the inverse is. So just take the formula k to the 1/2 times k to the 1/2 equals k. Take inverse both sides. Okay, you get k square root inverse, k square root inverse equals k inverse. And remember, AB inverse is B inverse A inverse, so I've swapped them. This k went here. Yeah? It's hard to tell, I know, but this k is that one, and this k is that one. All right, so what is the, let's see, the square root of the inverse? What matrix has the property that if I square it, I get the inverse? This is like so trivial, it's hard to even articulate it. So this is basically saying that, so here's a matrix, right? Call that like A. Okay, so A squared is K inverse, right? So A must be the square root of the inverse, right? So the square root of the inverse is the inverse of the square root, right? So K, take this matrix, take its square root, that's that. So that is K to the 1/2 inverse, right? Okay, so in the future, we'll just we'll write this as K to the minus 1/2. Okay, and if you don't show this, you gotta be careful. When you write this, it's okay, is this inverse square root or is that square root inverse? Because a priori, you maybe can get different answers doing the two things in the two different orders. But in fact, you get the same matrix in the end, depending whether you square root and inverse or whether you inverse and then square root. Okay, for just a fact that looks rather esoteric and technical right now, but we're going to use it in a hot minute. So consider this quantity. Actually, no, don't start with that quantity. Take what? Take this formula and just multiply both left and right by k to the 1/2. You get identity equals k to the 1/2, k inverse, k to the 1/2. If you want, you can also just expand the right-hand side in terms of the u lambda u transpose and get the same thing. Okay, so this is, let's call this equation 1. Well, I mentioned it only because we're going to use that fact very shortly. Lastly, this square root is positive semi-definite. How do I know that? It's a one-line argument for that. How do I know that? Sorry? Because k is K is indeed positive semi-definite, but I mean K1 half is a different matrix, right? Maybe you have it. I'm just making kind of a mountain out of a molehill here. So remember I said when I wrote up the linear algebra fact, I said K is positive semi-definite if and only if it can be written orthogonal matrix, non-negative diagonal matrix, the orthogonal matrix transpose, right? Here's a matrix that I can write as orthogonal matrix, non-negative diagonal, orthogonal matrix transpose. So this must be positive semi-definite because it has that structure. Okay. Good. Okay, so that's all the linear algebra background. So back to Gaussian random vectors. Okay, so now suppose X is Gaussian with parameters mu and k. Okay, I want to show that any x as Gaussian, okay, I can write as a linearly transformed standard normal vector. So to do that, take k and write out its expansion u lambda u transpose. Actually, I guess we don't even need the expansion when you come right down to it. So just take k, and then from that compute k to the 1/2, and maybe k to the minus 1/2. So to compute those, you would do the expansion, but you can view that as under the hood if you want. Okay, now here's the thing. I'm going to construct a new random vector in terms of x. So define z as a particular transformed version of x. So we'll let z be x minus the mu vector, and then times k to the minus 1/2. Okay. What is the density of z? Okay, we'll apply that fact from, okay, that fact from 3100 I had right here. I guess we used it twice. Okay, we used it before, and now we can use it right now. Okay, and then we're done with it. Okay, so density for z in terms of density of x, we're going to have k to the minus 1/2 with a determinant, and I'll have f x evaluated at this vector. Evaluated at k to the 1/2 z plus mu. Right? That's z in terms of x. Okay? All right, so let's plug in the density for x. So x is just the general multivariate Gaussian density. So 2 pi n over 2. We have determinant of k to the power 1/2, e to the minus 1/2, and then instead of x, I'm going to have this whole expression here. So k to the 1/2 z plus mu. That's like my x minus mu, right? You have x minus mu is what goes in the transpose. K inverse, and then the whole thing again. K to the 1/2 z plus mu minus mu. Like that, okay? It's a lot of writing. There's not a lot of logic in here, actually. So x is just a Gaussian random vector, so it has that density we started out the lecture with. Okay, the density for z, in terms of the density for x, is related this way, so just plug in now. Just plug in for fx. That's what you get. Okay? So this simplifies quite a bit. In fact, it simplifies a lot. Okay, so k to the minus 1/2 determinant is going to cancel this k to the 1/2, right? Using the fact that the determinant of the inverse is the reciprocal of the determinant. Okay, the mu's are gone, right? And what we're left with is 2 pi n over 2 e to the minus 1/2. And then AB transpose is B transpose A transpose, right? So you're going to get Z transpose K to the 1/2 transpose K inverse K to the 1/2 Z. All right? K to the 1/2 is positive semi-definite, so it must be symmetric. So the transpose is doing nothing. Tell me about K to the 1/2, K inverse K to the 1/2. What can I say about this matrix product here? K to the 1/2, K inverse K to the 1/2. Yeah. Sorry? Is identity? How do we know that? Yeah, that's 1, right? Wait for the camera to. Okay. Yeah, that's right here. Okay, this is this technical fact, and you're just then saying we'll use it shortly. So this whole thing is identity. So different color. Gone, gone, gone. Okay, and we get 1/2 n over 2 e to the minus 1/2 z transpose z. Okay, so this z vector is a Gaussian vector, parameters 0, identity. Okay, so given any Gaussian vector, I can transform it into another Gaussian vector that has parameters 0, identity. That's always possible. I just did it, right? I took any x, I found a linear transformation that would turn it into a standard normal Gaussian vector, okay? Which now means I can flip it around and I can write x in terms of a standard normal Gaussian vector, right? So x, we know we can write, just kind of invert this relation. X we can write as k to the 1/2 z plus mu. Okay, something big has just happened. Okay, this is an important landmark equation here. Okay, so any Gaussian vector we've shown you can write as a linearly transformed standard normal. Okay, so you take the standard normal, you kind of multiply it by this to give you the covariance. Okay, we don't know its covariance yet, but to give you the k parameter you want, and use this to get the mean that you want. Okay? Always possible. In some cases, z actually has, like if x actually represents some physical thing, some cases, z would actually have some physical interpretation. Like, z, you can often think of as representing like the kind of underlying independent degrees of freedom in the physical system. And then you're not measuring the underlying degrees of freedom kind of in their natural basis. You're measuring it in some other basis that kind of like mixes them together. And that's where you get the dependence. Okay, but given the x measurements, you can sort of like do a change of basis to get at the underlying, decoupled modes of the system, and that's what z represents. Okay, or you can just view it as a math statement. Okay, math statement is any x you can view as a transformed version of a standard normal z. Okay, so this has many uses, this formula. That's why I took the time and went through it. So having gone through all that work, we can now kind of reap the benefits. First of all, I'll say this is useful conceptually. This one right here. It allows you, it just gives you a way of thinking about a Gaussian vector. Like every Gaussian vector you come across, you can just say, oh, it's basically this. It's basically like a standard normal. It's like IID Gaussian random variables that have been linearly transformed. Okay, that's a useful way of thinking about it. In fact, this is the way I think about a Gaussian random vectors. You come to office hours and say, hey, Professor Wagner, I have this Gaussian random vector. Okay, in my head, I say, okay, we got this. Okay, little secret I'll share with you, the multivariate Gaussian density I wrote up at the beginning, I do not carry that around in my head. I don't have that memorized. Okay, I have this memorized. This is very memorable. This I carry around in my head 24/7. Okay, that multivariate density, whenever we teach a class like this where we need it, I cram it in my head before the lecture where we use it, and it stays in my head for about a week or two, and then I forget it. Okay, so if you come to me in November and say multivariate Gaussian density, I'm going to probably open up a book or just rederive it, to get it. This though sticks with you. So some people actually define a Gaussian random vector this way. Okay, they'll say a Gaussian random vector is just defined to be a random vector you get by taking a vector of IID standard normals and then linearly transforming it. That has some advantages. It's easy to remember. Okay, it actually generalizes quite well. So our definition only works when the random vectors are continuous. They have a joint density. Okay, this definition allows you to handle cases where you don't have the joint density. So there's that benefit. That's not really so important for us in this class, but if you're doing like a pure theory class, that can really make your life easy. So it's conceptually useful. It's also useful like computationally. So like for instance, suppose you want to produce in MATLAB a realization of a Gaussian random vector x, and you're given the parameters mu and k. All right? How do you produce a realization? If it was a standard normal, then it's easy. You call rand n a bunch of times. You get a bunch of Gaussian random variables. They're zero mean. They're unit variance. They're independent. Put them in a vector. You're done. That gives you a z. Okay? But suppose you have like an arbitrary k and mu, and you want to get a realization of that random vector. What do you do? Okay, well, if you can compute the k to the 1/2, just take the z you just created, multiply it by k to the 1/2, add in the that you want, all right, and then good to go. Okay, so that's one use of this. I'll show you a bunch more. I have like 5 of these, I think. So one is let's do away with the charade about mu being a general parameter and k being a general parameter. Mu is the mean and k is the covariance, and we can show that quite easily once we have this fact here. So suppose x is Gaussian with parameters mu and k. What is the mean and what is the covariance matrix of x? Well, okay, one option is to like integrate the multivariate density. Okay, you can just integrate that big thing and figure out, you know, what the mean and the covariance matrix are. All right, good luck. It's doable in principle. In practice, it's a big pain. But armed with this formula, it's like a one-line thing, painless, minimal calculation. Okay, so I know I can write this, right? Where z is a standard normal. I do know the mean of z, right? Z is like IID Gaussian random variables, zero mean unit variance, right? So this is 0. Likewise, kz is identity, right? Because I have a vector, independent components, each with unit variance. So the covariance matrix is going to be 0 off the diagonal, because the things are independent, hence uncorrelated. The diagonal is just the list of variances. Those are all 1, right? So I know these 2 facts, and then I'm good to go. So I'm in the clear now, right? So take mean of both sides. You'll get, if you want to write it out, k to the 1/2 mean of z plus mu. So that's mu. So the mean is mu. Covariance of x is so I guess we had this fact, and you can write out the definition of the covariance matrix here, but we had this fact that like, if y was ax, then ky is equal to a kx a transpose. That was the fact I encourage people to memorize, right? Okay, if you add a mean in here, it doesn't change anything. So if I just do like plus b, that doesn't change this fact here because in the definition of the covariance matrix, you subtract off the mean. Okay, so when you add a mean, you just end up subtracting it back off. So I can just put plus b here and it doesn't change the result. Does that make sense to people? You want me to show this? Or are people good with this? Hello? Are we good to go? All right. Okay, so if you use that fact, then kx is going to be a kz a transpose. A is k to the 1/2, right? Kz is identity. So I get k to the 1/2 times k to the 1/2 transpose. K to the 1/2 transposes K to the 1/2. It's symmetric. So all this collapses down to just K. Okay, so bottom line, yes, mu is the mean, K is the covariance matrix. We don't need to pretend anymore. Okay, second consequence. So if X is Gaussian with a diagonal covariance matrix, then the components are independent. Okay, in general, if you give me some arbitrary random vector, if the components are independent, then the covariance matrix will be diagonal, right? Because the off-diagonal entries are the covariances among the components. Those are all 0 if they're independent, okay? So independent implies uncorrelated, hence diagonal covariance matrix. This is saying the reverse. If it's Gaussian and the covariance matrix is diagonal, then they're independent. It's going the reverse way. So this you can also show from the density. It follows quite easily from this expansion though, because if K is diagonal, then K to the 1/2 will be diagonal, right? If K to the 1/2 is diagonal, then look at this equation here. The components of Z are independent, right? Z is just like, you know, independent scalar Gaussian random variables across the components. So the components of Z are independent. If K is diagonal, okay, then you've got like parallel, like there's no coupling among the equations here, right? Like the ith variable here is just a scaled version of the ith variable here plus a constant, and there's no mixing at all. So X would inherit the independence of Z when K is diagonal. Okay, so we can go from uncorrelated or diagonal covariance matrix to independent when things are Gaussian. So one way of thinking about this, so you know, covariance, so if the covariance matrix is diagonal, then all the covariances among the constituent variables are 0. Covariance is a moment, right? Covariance is a moment. Moments summarize distributions. That's why we use them. It takes some aspect of the distribution, where it's centered, how spread out apart it is, whatever, and just summarizes it into a single number. Okay, so covariance summarizes dependence in a way. Okay, kind of tries to measure dependence between two variables and gives you like one number that quantifies that dependence. Okay, but it's a summary. Okay, it's sort of collapsing this complicated phenomenon down to like one number. Okay, you can show, this doesn't follow at all from what we've done here, but if you take other classes in probability, you'll see that covariance in some sense captures linear dependence only. Okay, and that's why you can have dependent variables that are uncorrelated. If they have, in some sense, like kind of higher order nonlinear dependence, okay, then they'll be dependent, but the covariance doesn't pick it up because it only looks for linear dependence. Okay, so that's why you can have dependent variables that are uncorrelated. Now in the Gaussian world, like this is the Gaussian world right here. It doesn't get any bigger than this. So everything's linear. Okay, so it's impossible to have like random, like components of a Gaussian random vector that are dependent but in a nonlinear way. Either they're dependent in a linear way through this K, or they're not dependent at all. Okay, so that's why if in the Gaussian case, if the covariance says they're independent, then they're independent. Okay, because it's capturing everything. Okay, that was 2. 3. If X is Gaussian and you have some non-zero vector A, then A transpose X is a Gaussian scalar, a Gaussian random variable. Okay, so to show this, we use a fact that hopefully you covered in 3100 if you did Gaussian random variables. So if you have two random variables, x and y, and they're independent in Gaussian, then what can I say about the sum? Should we cover this in 3100? Two independent random variables, they're both Gaussian, I just add them. What can I say about the sum? Did you not cover this? It's what? Gaussian. Yeah, it is Gaussian, yeah. Is that why you're not talking? Because it's like so obvious that no one wants to say it? Hello? Yes, it is Gaussian. The mean of this will be the sum of the means. The variance of the sum will be the sum of the variances because they're independent. And this will be Gaussian. So there are various ways of showing that. It's, you might have seen that the PDF of the sum of independent random variables is the convolution of the PDFs. And the Gaussian pulse has this property that when you convolve it with itself, it gives you back itself. Like it's a fixed point of the convolution operation. You do it with like moment generating functions and characteristic functions as well. Anyway, hopefully you've seen this somewhere. If not, just take it for granted as a fact. Sum of two Gaussian random variables is a Gaussian random variable. Be careful, the sum of two Gaussian PDFs is not a Gaussian PDF. I mean, it's not like, if you have a Gaussian PDF like that and a Gaussian PDF like that and you average them, okay, you don't get a Gaussian PDF. You get a two-humped thing, right? Okay, so you got to keep straight. Adding the random variables, which means convolving the PDFs versus like adding the PDFs, which is like what you get if you flip a coin and take one random variable with the other depending on the value of the coin. Okay. All right, so with that fact, we can prove number 3. So again, just write x as k to the 1/2 z plus mu. So then you have A transpose x is A transpose k to the 1/2 z plus A transpose mu. And just call this whole matrix like B transpose, let's say. So you get B transpose z plus A transpose mu. Okay, so this scalar, A transpose x, that's a scalar random variable, right? That's a sum of independent Gaussian random variables plus a constant. And the constant is just shifting the mean around, right? So all the real work is happening right here. Okay, so that's Gaussian. And that's it. Okay, so we're using the fact here. We're using the fact that when you add up components of z, so z has IID Gaussian components, right? So by this fact, when you add them up, you get a Gaussian random variable. And that's what we're doing here. Okay. In particular, if you choose like A to be like 1, 1 in it like this, right? Then you get that if you have a Gaussian random vector, each component is a Gaussian random variable. But it's saying more than that, right? It's saying like somehow like a Gaussian random vector kind of looks like a Gaussian scalar in every direction. No matter what direction you project in, you get a Gaussian scalar. Okay? So it's more than stronger than this. In fact, you can construct examples where the random variables are marginally Gaussian. Each is Gaussian, but you put them together and do not get a Gaussian vector. Okay, which is basically saying that this condition holds for A of this form, but not general A. There are other directions you look where it doesn't work out. Okay? This is also, by the way, another equivalent definition people will use for just Gaussian random vectors. Say a random vector is Gaussian if it looks Gaussian in each direction. If it looks like a Gaussian scalar in each direction, you can project it. That's another equivalent way of doing it. By the way, when I first started teaching, I used to use these kinds of things as definition. I define Gaussian random vectors this way or through this kind of relation right here. Because conceptually it's like so much cleaner and the properties which are what you really need follow a lot easier from this or from this even compared to the density. So I used to do it that way, and like I was very pleased with myself for coming up with this like pedagogically superior way of doing it, and like the students did not like it. Because typically you come out of a class like 3100 and you're used to saying, okay, an exponential random variable is one whose density is this, the closed form formula, right? Gaussian, density is this. Geometric, PMF is this, okay? So this idea where you sort of define a distribution through its like implicit properties, just people got uncomfortable with. So I fought it for a while and then I gave in. So now we define a Gaussian vector as one whose density is that big mess, okay? But you can see my bias, okay? This is the way I think about it more in terms of things like this. Okay, what are we on? That was 3, 4. Okay, let's do a matrix generalization of this fact here. So if X is Gaussian, mean mu covariance matrix K, and A is an invertible matrix, B is a real vector. Then if you let Y be AX plus B, okay, such that Y will be Gaussian. Its mean has got to be A mu plus B. And the covariance matrix is going to be A, K, A transpose. So this, you can show this from the, using the density if you want. I mean, we've done similar calculations already. I think an easier way is just, again, use this decomposition in terms of Z. So write X like that. And then Y becomes AK 1/2 Z plus A mu plus B, right? Okay, and then we showed our third example was if you have a random vector that's like a matrix times standard normal vector plus a constant, then Y is Gaussian with these parameters here, A mu plus B, and then covariance matrix will be this one times itself transpose, which is going to give you K, A transpose. Okay, so I'm skipping some steps here. This is similar to the stuff we've done before. Okay, last point I want to make. This is what, 5? Okay, suppose I take a Gaussian vector. I take its Carhunian-Loew transform. So Y is U transpose X, where U is basically the eigenvectors of K. So K is U lambda U transpose. That's the KL transform. Then the components of Y are independent. Okay, so in general, when you take the Carhunian-Loew transform, you take a random vector, you map it to one whose components are uncorrelated. Okay, when everything's Gaussian, you can say more. The components are actually independent. Okay, by the following reasoning. So y, if you apply the previous fact, okay, y is going to be Gaussian with mean u transpose mu. And then covariance matrix U transpose K U. But U transpose KU is just lambda. Right? Because K is U lambda U transpose. So my Cahuin-Love transform is Gaussian and has a diagonal covariance matrix. So therefore the components of Y are independent. Okay, so the Cahuin-Love transform is like particularly powerful in the Gaussian case because it takes your vector with like arbitrary dependence among the components, transforms it into one for which the components are independent. And you can always go back. You just invert the transform to go back. Okay, so calculations are a lot easier when the components of your vector are independent. Like a general strategy for handling those is to apply the KL transform first and then do the calculation in that new domain. Okay, and there are various applications where one does that. I mentioned them when we first introduced that transform. That's it on Gaussian random vectors. That's all I have to say. Other questions? So that's the end of that. It's like approximately half of our probability review, or background. All right, so we have a few minutes left. Let me just introduce Bayesian inference. It's actually kind of a lead up to that before we start doing any real math. So we can do some of the lead up today, and then we'll pick up the math on Monday. Assuming no questions about Gaussian? Okay, we can talk during office hours if you want. Okay, so Bayesian inference. So remember my general strategy on this probability review, I'm not doing like a full-on probability review. I'm just kind of zeroing in on the parts of probability that we will use a lot that are not necessarily emphasized in your earlier classes. So you probably did some, like random vectors or like multiple random variable studies, but you probably didn't drill down into like covariance matrices and Gaussian stuff the way we have here, and we're going to use that. The other half of the probability that we'll use a lot is Bayesian inference. Okay, so talk about that now. We're switching gears. This is like completely different stuff compared to all that Gaussian work. This is much more discrete in nature, whereas all that's continuous. Okay, so some general comments first. So to infer means to deduce from evidence. And the way we'll formulate the problem we'll say given two random variables, x and y, our problem is to infer, i.e., in low-tech terminology, just guess the realization of x from the realization of y. Okay, so it's sort of a contrived example if you want to link it to this Gaussian stuff. So suppose, in MATLAB, you produce your Gaussian random vector. Say it has two components, okay, and you have both of them in MATLAB. And you take the first one and you show it to me. Now I have a real number sitting in front of me. And you say, guess the second component in the vector from that, okay? So that's a game we could play. That's a contrived game. But that fits within our inference framework. That's the way we're going to think about inference. There are two random variables. You observe the realization of one. You want to guess the realization of the other. Okay? This crops up in a lot of different physical situations. So one that's particularly important for us, digital communication. So there, think of x as being the channel input. or like the data that you're trying to transmit. Think of Y as the channel output. Okay, so if you're on the receive side, okay, you're going to get the channel output, and your job is to infer from that what the input was or what the data was. Okay, so if you're the base station, to give sort of anthropomorphize, is that a word? The base station. So if you're the base station, okay, then you pick up this like electromagnetic wave, okay, and that wave was sent because someone's trying to send a text message, and the ASCII text was encoded in the electromagnetic wave in some complicated way, and the wave got attenuated and it ricocheted off things and superimposed with itself and so on. You get this like messy thing, okay, and from that you want to infer what the text message was, okay. That's like the receiver design problem right there. Okay, on some level, like digital communication, at least the receiver side of digital communication, design the receiver is like one big inference problem. Okay, you get one random thing, you want to guess the other. But it arises in a lot of other places too. I don't know, spam filtering. So X there is just like, think of it as like a binary random variable, 1 or 0, depending on whether the email is spam or not. Okay, and then Y is like various attributes that are kind of easily observable. So it's the headers. Is the email in all caps? Does it have lots of $signs in it? I won't. There are many other attributes you can probably think up that we don't even want to write on the board. Did it originate in Florida? Like, wasn't Florida like spam capital of the US for a long time? Probably now it's more like Ukraine, or I don't know. Okay, so if you're designing the spam filtering algorithm for Cornell, okay, you observe various things about the email, okay, and from that you want to infer whether the email is spam or not, right? Filtering, denoising. So X is like the original uncorrupted signal. And Y is the noisy observed version. Okay, so you don't observe the uncorrupted version, you've got the one with noise in it. And your job is to infer what the original one was from the noisy version. Okay, so you take this like LP out of your parents' attic, or maybe your grandparents' attic. I would pull it out of my parents' attic, maybe it'd be your grandparents' attic, I don't know. And you just like play it on a record player, and you get this audio recording with a huge amount of static in it. Okay, and then you're going to try to denoise that to get the original one. Okay. Many others, so like, I don't know, handwriting recognition. Okay, so you want a machine that will automatically read people's handwriting. So there, for a particular letter, X would be like the letter of the alphabet this represents. Y would be like the pixelated image of it. Okay, you want to design an algorithm that will identify the letter from the image. Okay, much of machine learning is just inference. I shouldn't say just, but much of machine learning is inference. Okay, so taking machine learning classes, it's going to be a lot of this stuff. Just one comment or one point to think about over the weekend. We're going to assume that both X and Y are random variables. We're going to treat them both as random variables, so they're kind of on equal footing in some sense. They're both random variables. I observe one and want to guess the other. It's debatable whether it's reasonable to treat X as a random variable in all these situations. Like this one, for instance, whether an email is spam or not. Like whether an email is spam or not is not random the way like noise on the oscilloscope is random, right? Here too, the input is chosen by your encoder. Like you're designing the encoder that's actually constructing X. So does it make sense to call that random? You know, here maybe it's a little better of a fit. Okay, but it's not entirely clear that you should really view as proper to view x as a random variable the way, you know, noise is random. Okay, so that's where the Bayesian part comes in. So Bayesian just means you treat it as random even if it's not really reasonable to call it random in the end. So anyway, I'll kind of leave that for food for thought over the weekend. So on Tuesday, we'll pick it up here and we'll set this problem up carefully and then talk about how to actually guess one random variable from the other. I have office hours right now if you want to chat about homework or whatever. I'll see you Tuesday.